Okay, so this is 5.4 using graphs. So we just reviewed all of that stuff, and now let's get to 5.4. Not going to give you homework over this section. If you were on Info Direct, you'll notice there's no homework tonight. I know you're excited. So, but graphs are often used to illustrate relationships between variables, between quantities, between concepts, etc. So the whole purpose of lesson 5.4 is to begin to get a good grasp on what things a graph gives us. More and more today, we are looking for students to be able to interpret and read graphs and understand what they represent and what they mean. And so never, more now than ever before. And I've been doing this 30 years, and we really today want students to understand graphs. If you look at this graph, somebody tell me, what are the units of the independent variable? What are the units of the independent variable? Anybody? Josh? Age is the concept. What would the units be, Josh? Years. So here's what Josh did. I think Josh did something like this in his brain. Independent variable is the x. The x-axis is there, and the x-axis deals with age or years. Okay? Therefore, the dependent variable units are inches, right? Because this is the y-axis, right? So the independent variable is age in years, and the dependent variable is length in inches. Growth of a largemouth bass. How come there's no negatives on this? Because how long was the fish before it existed? All right, it was not. Okay, there is no negative time. All right, we got a problem there. Okay, so it's just trying to plot the situation throughout its life. And in this scenario, what age was the fish on the last piece of data? I'll give you a second on 3. Tell me, what age was our largemouth bass on the last piece of data? What was its age? Here we go. 1, 2, 3. 6 years old, right? 6 years. And in this graph, they gave with the point the coordinates, which makes life easier, so you don't really have to guess. Now, in some of them, it's not that big of a deal. In this point, it's right on the intersecting of the axis, right? So we can clearly read 2 years and 11 inches, right? Pretty easy. But on a point like this, well, you got to guess that it's dead center halfway between. Now, we can read 6 years pretty easily, but you have to guess that it's at 17 and a half. By then putting the coordinates there, it allows you to read an exact situation. Okay? So independent variable is always the x. Dependent variable is always the y. And look, the thing grows as a function of time. As time goes on, the fish grows longer. So the length results from the amount of time. So time is the independent variable, determining then the length, the dependent variable. Okay? Any questions on that? Anybody? Any questions? Okay, let's go to the second situation. First class postage rates. So first off, you got to understand the scale. So our independent variable units are years, and our dependent variable units are cents. So it's the year of the price versus the stamp's cost in cents, right? And again, the cost of the stamp depends upon what year you're talking about, right? So it's the dependent variable. The cost depends upon the year. All right, and if you looked at your scale, every little mark is how many years? 5 years. So that's 1855, 1860, 65, 70, 75, etc. By the way, notice how the scale stays uniform. Every once in a while, I get a student, a slash mark is twos, and then all of a sudden the next slash mark becomes a 5, and the next slash mark becomes a 30. You can't do that. You got to keep your scale uniform. All right, every slash is a 5. Don't be messing up your scale. Now you can make every slash mark a 10 and everyone's a 10. That's fine. You make every slash mark a 50 and everyone's a 50. That's fine. But you can't make the first two ones and then all of a sudden have the same gap and call it 5, and then have the same gap and call it 30. It's got to stay uniform. Follow, otherwise you are skewing your graph. You don't want to skew the graph. You'll hear me say that. It's just like a picture of you, photo, right? What happens if you take the photo and you squeeze it in at the sides? You get what? Squeeze it in at the sides, you'll get thinner. If you pull it out at the sides, you'll get fatter. I never pull mine out at the sides. If you pull it up at the top, you'll get thinner, right? Taller and thinner. But if you scrunch it down at the top, you'll get shorter and fatter. All right, I always stretch mine and squeeze in the sides if I need to. All right, anyhow, you don't want to skew it by trying to change the scale. It would throw everything off. All right, so again, I'm not going to go through the same thing here. It's your X. That's your Y. You can notice, though, at a quick glance, what happened to the price of stamps. Looks like they were about 6 cents, maybe 5 cents there. And they went down to like a penny, maybe 2 cents. And it was down there all the way through. Look, 1975, a stamp was like 8 cents. And now it's up, what, 43 at 2010? And what is it now? I don't even know. First class stamp. Who knows? Right? Okay. Yeah, you guys have this in your notes in front of you. Might be a little bit easier to read than the screen. Let's answer a couple questions. Use the graph to do the following. How far has a skydiver fallen after 5 seconds? Don't say anything. How far has the skydiver fallen after 5 seconds? Ethan, go ahead. It is 500 feet. Ethan went to 5 seconds and looked at the distance. And he said feet because he looked at the scale and saw the scale was in feet, right? And you would too, wouldn't you? How long does it take him to fall 2,500 feet? Is your answer going to be an estimate or exact? Estimate, right? Because hopefully you went to 2,500. You say I'm right here. What are you going to call that? I called it 17. I'd let you say 16. I definitely wouldn't let you say 18, right? Because 18's past halfway and it's definitely not past halfway, right? Makes sense? So there is a little bit of guesswork on that one. What does the change in distance divided by the change in time represents? What does the change in distance divided by the change in time represent? I'm going to do this one for you. The change in distance divided by the change in time. I'm going to take, let me erase my picture here. I'm going to take this point right here. What is our distance right there? 500. And I'm going to go to this point. What's our distance there? What's the change? How much did it change? No. We went from 500 to 3,000. From this point to this point, how much did it change? 2,500. All right? It went from 500 to 3,000. Did it not change 2,500? That was the change in distance from those 2 points. I'm going to stay with the same 2 points. How much did the time change? 15 seconds. Here, and I'll put my feet here. So what is our change in time divided by our change in distance divided by our change in time? 2,500 divided by 15. Let's see. Does that have 5 definitely goes into 2,500. I'm just going to use my calculator, make it easier. 167.7. All right, if we were to reduce that, we get a nasty thing. I'd have to sit and reduce to 5. I don't have time at your quiz coming up. But here's the reality. For every 2,500 feet of going up, you go to the right 15 seconds. And there's a ratio there. What's 2,500 divided by 5? It's 500, right? So if I reduce this, this would be 500 feet to every 3 seconds, right? I factored the 2,500 into 5 times 500. I factored the 15 into 3 times 5 and reduced it. Yes? You guys okay? For every 500 feet up, we gain 3 seconds. So watch now. Don't do this on your picture. Just watch. I'm going to start here. You see where I'm at right now, guys? I'm going to go up 500 feet. How much time was that? 3 more seconds. We went from 5 to 8. I'm going to go up 500 feet again. I'm going to go over. Now what am I at? 11 seconds, right? 3 more. Every 500 feet up is 3 more seconds. Now I'm at 14 seconds. 500 feet over, I'm at 17 seconds. 500 feet over, I'm at 20 seconds. See, that part of the line is a straight line. This is called the slope. We're going to deal with that a lot real soon. The change in distance divided by the change in time is called the slope. We'll talk about that a lot here real soon. All right, you got to get going. So I want to get your quiz in your hand here soon. Describe the fall by looking at the red line of the graph. Okay. You'd have to break it up. Between 0 and 5, it's sped up. This curve kind of curves up, so it's speeding up. But from 5 seconds to 20 seconds, the fall was a steady rate. That's what this straight line represents. You say, Mr. Scarfe, I wouldn't have known that. Yeah, I understand. I understand. This fall, he hits a terminal velocity at this point now. The rate is a little bit less. It's decreasing. We'll deal with that more later on. I don't have a lot of time to deal with it now, so I'll come back to it later on, and we'll see other graphs, and we'll deal with it. All right, I want to look at 3. 3 is doing mountain hiking, and the first graph is time and heart rate. So notice the heart rate goes up steeply in the beginning, right? Then the heart rate stays the same. Yes? You guys are better off just looking. There's nothing to write on. I'm talking. I'm teaching you. You're going to put arrows on there. You won't even know what they mean. Watch, okay? Right here now, his heart rate goes steeply down, right? When does your heart rate go down when you're hiking? When it's easier, right? Let's start looking at the elevation. Notice in the beginning, he's going uphill. What happened to his heart rate? It went up. Now he's on a flat part, and his heart rate stayed the same. Then he went downhill. Isn't it easier going downhill? His heart rate went down, etc., etc. There's a correlation between the two graphs. One is showing time and heart rate. The other is showing time and the altitude, whether he's going uphill or downhill. And there's a correlation between the two. So that's 2 ways of showing the same situation, different data. Time in both cases, one heart rate, the other is altitude. All right. Real quick. Daily savings account balance. All right, look at this guy. He started out with so much money, right? This is money. And it's the same all the way to here, right? What must have happened right here? What must he have done? He put more money in his account, right? And now the amount is all the way to here. What happened? He put more money in again, right? Now he's got this amount. What happened right here? He spent some of that money, and now he's way down here, all right? We know that from the situation of days versus the balance. All right, last one. This one's neat. This is a bouncing ball. Oh, I know you can't see it, but I'm going to bounce this ball on my desk and see if it kind of mirrors that a little bit. So I hit my stapler. Did you see that? That shape? It was there. I'm not going to go after it. Time's sake. So it's just showing, it's mirroring what happens here with a bouncing ball. All right, that's the idea. We started at some height. It went down to the ground. It bounced back up. First bounce is the highest bounce back up, right? And it keeps getting smaller and smaller until it finally hit. We represent it with the graph. All right, that's all I'm going to do today there. Grab a cover sheet, grab a calculator, grab your brain.